Good morning, good afternoon, or good evening, wherever you are located. And thank you for joining us here today on Wednesday, the 18th of May. And we're going to be discussing AMETEK solid-state controls, how does an inverter work webinar. But before we go any further, if you would like to put in the chat bar on the right-hand side whether you can hear me or not, that would be extremely appreciated. So I'll just wait to hear if you can hear me, and then I'll go through what we are going to discuss today. Give everybody a moment to get in. Okay, thank you very much, Brooke. Says that you can hear me loud and clear, which is always a good thing. So while everybody joins the presentation, I'll go through the introduction. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid State Controls. I'm located in the Stafford office, which is just south of Houston, Texas, in the USA. I have 20 years in the industrial UPS industry, and as you can tell from my accent, I'm not from round these parts. I'm actually from Scotland originally, and I did 10 years in the North Sea, going around oil platforms, working on all different kinds of UPSs and chargers, which leads me on to the next bullet point. I have worked with all of the major UPS charger manufacturers, so I have a good idea of how they all work. Regarding the webinar, there will be a lag of around 30 seconds between you hearing my voice and me seeing a question. Basically, the platform that we use is Webinar Jam, and Webinar Jam has to take the signal that I'm putting in, and then it's got to do all the coding for iOS devices, Android devices, and Windows devices. So that processing time is about 15 seconds. So when I say something, you're going to hear it 15 seconds later. So if you type in a question, I'm going to see it 15 seconds later after I've said something. So what I tend to do is I try to leave the questions until the end because of that delay. But if I do see something pertinent to what I'm talking about in the chat bar, then I will definitely try to answer it as we go through. So hopefully I explained that in a relatively okay way. Webinar Jam, this platform has a panic button. Basically what it does is if I see in the chat bar, or if something seems to go wrong with this presentation, I can press the panic button. And what Webinar Jam does is it creates a whole new room, invites everybody into that room, and we start off from where we left off. So that should work if we need it. Another common question is, will the webinar be recorded? And the answer to that question is yes. If you registered for the webinar, then you will get a link after the webinar is complete of the recorded session. It takes a little bit of time. I can't remember exactly how long it takes, but you will be sent a link. The problem with that link is it's still within Webinar Jam, and it treats it as a brand new webinar. So when you press play, you can't fast forward and rewind. You can pause, I think, but you can't fast forward and rewind. So if you want to go to a certain part after you watch this and recap something, it's not the best thing to do that. So what our fantastic marketing department do is they convert that recording into an MP4, and then they upload it to the AMETEK Solid State Controls YouTube channel. And that takes about 24 hours for us to do that. And then you can go there, you can play it, you can share it, you can do whatever you want with it, fast forward, rewind, and all that kind of good stuff. The other popular question that we get asked is, can I share the presentation? Unfortunately, the presentation is proprietary. I cannot share the presentation. But like I said, if you go to the YouTube channel 24 hours after this presentation, you can watch the whole thing. You can share it with your friends and colleagues. So that's as good as getting the PDF. And the last thing that always makes me smile is the webinar should last around 1 hour. I do really try to keep it to 1 hour, but sometimes I just get so involved in a question or in a subject, and I just talk for ages, and I apologize in advance because I really enjoy this stuff. So my aim is to make it last an hour, so I'm going to do my best even today. Okay. So let's get started. So today what we're going to do is go over basic inverter design and help you understand basic inverter design. And then we will discuss the two designs of inverter bridges that AMETEK SCI use in the majority of their bridges. We will discuss the components used in that inverter bridge, and we will explain the benefits of each of the designs. Okay. So the first thing is, what is an inverter? And before we go any further, it's an extremely important thing we have to know. And in its simplest terms, it converts DC to AC. Don't get it confused with a rectifier, which converts AC to DC. So an inverter, we have DC going in here. Excuse my bad drawing. Let's say it's from a battery. Okay. And then that gets turned into a beautiful sine wave on the output. As you can see in this box here, we've got DC there and we've got AC there. So in its most simplest terms, it converts DC to AC, and it's used in UPSs, it's used in solar arrays for your house. If you've got solar panels on your house, then you will have an inverter to convert the DC that the solar panels generate back into AC. It's used for many, many different things. And even a variable speed drive is a kind of inverter. It does take DC and converts it into AC, but it's variable frequency AC that generates. Hopefully I haven't confused things too much. So before we get started with our design, I always like to try to explain something in a physical way. In most of my presentations, I try and use water analogies, but in this circumstance, I think the best way to explain how an inverter works in its most simplest form is by using a DC motor, okay, and some switches. So you can see here this circuit on the left-hand side here. This is either a battery or it could be a DC power supply, but it is DC that we have on the left-hand side here, okay? And we have positive at the top and we have negative down the bottom. And then this arrangement on the right-hand side, so let's circle it. This arrangement here is called an H bridge. And if you can't see it, it's because it does actually look like an H or H, whichever way you say it. Okay, so that is the basic design of an H bridge, and that becomes important when we move through into the actual inverter design. And we have four switches. We have switch 1, switch 2. So these two, switch 1 and switch 2, are in series, and switch 3 and switch 4 are in series. Okay. And in this first example, switch 1 is closed and switch 4 is closed. So that puts positive onto this side of the motor and negative onto this side of the motor, whether that's onto the brushes on the DC motor. But that's the orientation of the polarity of the motor. And that will make the motor spin in the clockwise direction. Okay? Very simple. All we do is close switch 1 and switch 4, and we will have the motor spinning in the clockwise direction. But let's say that what we need to do may need the motor to spin in the counterclockwise direction. Well, with an H bridge, we can do that very easily. What we can do is we can open switch 1 and switch 4, and then what we do is we close switch 2 and switch 3. So you can see here now, instead of the positive going down through switch 2, we're now going all the way down along here through switch 3. And then we get the positive to this side of the motor, okay? and the negative is connected down here through switch 2. So we have the negative. So that makes the motor spin counterclockwise. So with 4 switches and an H bridge arrangement, we can make a motor spin in 2 different directions. Very, very clever and a very, very simple circuit. Okay, so hopefully everybody is following me. And what I'll discuss on this next slide is the downfall of an H bridge. And the downfall of an H bridge is very bad things will happen if you close S1 and S2 together, because remember I said that they're in series. If you close those together, that is a direct short across the battery or the DC power supply. Okay, and if you have no protection, usually you would actually have a fuse here, to be honest. But if there is no fuse, the weakest part of that circuit is going to give up, and that's usually a wire. A wire will burn through or something like that, and it's called shoot through. That's the common term for it, and basically all the circuits in an inverter bridge will prevent S1 and S2 closing at the same time. And in truth, S3 and S4 is identical. If they both close at the same time, you will have a direct short across the power supply and bad things will happen. So don't do it. Okay. So in the previous slides, we're using switches. Okay. Switches are mechanical switches. And whenever you make or break an electric circuit, when there is current flowing through it, then you're going to get an arc. And that arc can pit and corrode the contacts of that switch. And also, a switch is mechanical, and therefore when you tell it to switch on, there is always going to be a delay from when you tell it to switch on from when it does switch on. And the same with it switching off, whether you use relay coils or whatever. Switches just aren't reliable for an inverter because we're going to be switching it at high frequency. So switches cannot be used in an inverter bridge. So the component of choice that we use is an IGBT, okay? And it's IGBT or IGBT, depending on how you've been taught, is an insulated gate bipolar transistor, okay? And this is a symbol diagram for it, and it has 3 connections. It has a gate, it has a collector, and it has an emitter. Okay. Now, ignore this diode for the moment. I will discuss this, but just pretend it's not there just now. This is actually the IGBT, this part here. Okay. That is basically what we're doing is we are controlling whether the collector and emitter become an open or a short by sending a signal to the gate. And I've got a couple of analogies that will help explain this. This diode here is actually just installed. It's not installed. It's manufactured into the IGBT, and it's called a flywheel diode. And basically what it allows to happen is if there is current flowing through an IGBT and you suddenly switch it off, there's going to be an inductive kickback. And basically this will go positive with respect to this. And what this diode allows to happen is instead of that positive to negative inductive kickback, which can be quite high voltage, instead of that damaging the IGBT, this diode allows that energy to be dissipated back into the circuit through that diode. In normal operation, this is a blocking diode. So when this is positive and this is negative, current can't flow through there. So it's as if it's not even there. It's only there to dissipate inductive stored energy when you switch off an IGBT. So you can really forget that it's even there, to be honest, in most cases. So my first analogy is the most simplest. Obviously, don't touch electricity. I know that's the world that we live in, that I've got to state the obvious, but this is just an analogy. And we have our gate here, and we have our collector and emitter terminals here. So let's say that this is connected to the positive side of something. And then let's say this goes down to let's say that that's actually a lamp. I've drawn it as a resistor, but let's make it a lamp, and that goes to the negative side of something. What will happen is if we send a signal to the gate, in other words, somebody pushes their finger on this spring-loaded push button, which is open just now, if we send a signal to the gate and we push that push button, we close the circuit there and the lamp will light. Relatively simple. And then if we remove the gate signal, then the spring will push the switch backwards, and there will no longer be a connection between the collector and emitter. So if we draw the lamp back in there, positive and negative, with no signal, there is no connection between the collector and emitter. So the lamp here will not light. Okay. So that is the basic fundamentals. Obviously, inside an IGBT, there isn't a spring, there isn't a switch. It's all done using semiconductors. There's no moving parts in it whatsoever. So this is just an analogy, remember? And the other analogy for those in the pump world or the pipeline world where there is fluids involved is a solenoid valve. Okay, so you can see on the left-hand side, we have the gate here, which is the connections to the magnet at the top. So these orange parts here, this is a magnet. And then we have the collector on this side, and we can see that there is fluid in here. And then we have the emitter on this side, and there is no fluid on this side just now. And you can see that there is a gap here because the spring for the plunger has pushed the plunger down because the armature has not received a gate signal. Hopefully you're following what I'm trying to say here. So the plunger has sealed this point here, so the fluid cannot flow from the collector to the emitter. But on the right-hand side, we have sent a signal to the gate. So we have pulled in, using magnetic force, we have pulled in this plunger, and the plunger has moved up and has opened this gap here, and now fluid can flow around there from the collector to the emitter. Okay, once again, there are moving parts here and there is fluid involved here. This is just an analogy. It's basically to show you how an IGBT works and hopefully get that process going in your head for what it is. And what we use it for in inverter technology, an IGBT is used as a switch. It is either on or it is off. It's not used in any amplification region, or it's not doing any fancy other stuff. It is either on or it is off. It is very, very simple. Okay. And this is what IGBTs kind of look like, especially the ones inside of our inverter. They're high powered, so obviously they're usually 100, 200 amps, maybe even more that they can handle. On this one here, this is probably the collector and the emitter, or it could be the other way around. And then we have our gate signals here. In truth, that's probably the emitter and that's the collector, because this is also the emitter, and you send a signal between the gate and the emitter terminals here, and it will allow power to flow through those two terminals. That's the same with this one down here. The one in the top right is a little bit different because there's actually two IGBTs in there. I know it's difficult to see on this slide, but there is an IGBT there and there is an IGBT there. Okay, so one will be the collector, one will be the emitter, and then the other one will be the collector. Okay, and then we have our gate emitter terminals here. Okay, The two devices are completely isolated from each other, except for that one connection between the two devices, but it does allow you to connect these in different varieties inside the circuit, and you'll see that as we move through. Okay. And then the base of these IGBTs are flat metal, and it's heat conductive metal. There is no electrical connection between these terminals here or these terminals here down to the actual physical base of this. The physical base of an IGBT module like this is there to dissipate heat onto a heatsink. So these IGBTs will always be mounted flush to a heatsink using white non-electrically conductive heatsink compound. Okay, the heatsink compound is only there to transfer heat very easily. And this is what you should not do. Unfortunately, IGBTs are extremely sensitive devices to high current situations. There is no fuse that has been invented that is quick enough to, if for some reason there is, you get a shoot through circumstance where both IGBTs in one leg are turned on at the same time, then there is no fuse quick enough to prevent that high current from damaging the IGBT, and this is what happens. Obviously, this is an excessive detonation of an IGBT. In some circumstances, you won't even see the physical damage in an IGBT that has failed. But in most cases, you will see some cracks in the external cases. Okay. So the first inverter bridge design we are going to discuss today is in what we call at AMETEK Solid-State Controls the DSE model. Okay, that is our digital digital ferroresonant inverter technology, and I'll explain that in just a moment. I'm going to take a drink. So this circuit here, it looks a little bit complex, but I've broken it down on this one here. So if you can see, we've got our positive in, we've got our negative in, and then we have two IGBTs, and then we have a transformer here. And we're using the center tap of the transformer here for this simplified circuit. And if I go back to the actual circuit, it's exactly the same here. We've got our positive and we've got our negative. Switch 1 and switch 2 are our IGBTs, center tap of the transformer, and then the output of this is a very complicated ferroresonant transformer. Okay, so that looks complicated, so we will deal with the simplified drawing. Okay, so what you can see is if we turn Q1 on now. Before I go any further, this is not an H-bridge design, which I discussed earlier. This is a different design using the center tap of a transformer, which is actually even more simple. So if we turn Q1 on, this positive is allowed to go down here to the center tap of this transformer. So we are making the center tap of this transformer positive with respect. If we turn this on, we follow that through and we go down through Q1 down to the negative. So our negative is here. The switches are short, so that means our negative is here. Okay, so when we turn Q1 on, we are getting a negative pulse with respect to the center tap of this transformer. Okay, and then we turn Q1 off and we turn Q2 on. Our positive is allowed to go down, doesn't change, to the center tap of this transformer. But then remember to have current flow, you have to complete the circuit. You have to go down through this transistor here up to our negative. So that makes this negative and that makes this positive. So that gives you the positive side of that square wave. Okay. So what we can do is by switching Q1 on and then Q2 on, if we do that 60 times a second, we get a 60 hertz square wave on the primary of this transformer here. Just going on and that's off, and then switching it round, that's off and that's on, and just doing that 60 times a second, we create a 60 hertz square wave. Very simple. And then on you can see here that the dot for the transformer is at the top here. So let's say we were putting 100 volts in here. We are getting a 100 volt peak to peak sine wave. So it's actually, sorry, not peak to peak, peak sine wave, and peak to peak is going to be 200 volts. Okay. Not sine wave, sorry. It's a square wave. Everybody's shouting at the screen. I'm not perfect. Okay. So that's how simple it really is. Now, when you place it inside one of our drawings, it can look extremely complicated because there's so many other wires connected in there. There's a control board up here. We've got a static switch here. But here is our inverter bridge right here inside one of our DSE systems. And what you can see is this is our positive. So forget about the breaker and everything just now and the fuse. We are going here and we're going down here, and look, we are going to the center of that transformer. It's exactly the same as the drawing that I just showed you. And in this drawing, we have two IGBTs in parallel because we obviously needed more current in this system. And that's all we do. If you want a higher kVA inverter bridge, we will just put more IGBTs in parallel to give you the current that's required. So you can still look at that as one switch, Q1, for example, and then this one is Q2, okay? And as you can see, we're still going down through that, back to the negative on that one, and back to the negative on that one when necessary. So it is exactly the same as that simplified drawing that I gave you. On the ferroresonance system, what the ferroresonant transformer does is using a tank capacitor, which is there, and some inductive reactance in all of these windings here. What a ferroresonant transformer does is it creates a constant voltage transformer. What we do is we actually saturate the core of this transformer using this capacitor here, so that for a certain amount of voltage going in, so basically we can probably say you could have anywhere between 100 and 140 volts going into this transformer, the output is going to be exactly 120 volts due to the nature of that transformer. Okay, and not only does it become a constant voltage transformer, using the choke and the inductance, it actually changes that square wave into a sine wave using the inductance and capacitance. So it takes out the majority of the harmonics of the square wave and turns it into a sine wave. A very clever thing, a very simple thing in what it does, the CVT or the ferroresonant transformer. Now, the only control that we have for the IGBTs in our ferroresonant inverters is we can change the area under the square wave. Basically, we can tell the IGBT when to turn off, okay? So you can see in both examples here that that's turning on at the same time and that's turning on at the same time. You can see here that that one's turning off at a different time from this one. This one here is still turning on at the same time, and the trailing edge there is different. What we're trying to say is we can move that trailing edge. And looking at the top, pretty much we're saying that between 140 and 105, the area under the curve changes. Okay, at 140, we have this additional area here. And remember, you can put your batteries on equalize for a 60 cell system. That will take it up to 140 volts. So we have to allow for that. And also your batteries can discharge all the way down to 105 volts, which is this point here. So the area under the curve changes if we don't control the trailing edge of the signal. So what we can do is for 140 volts, if somebody puts a system in equalize, we can switch off the IGBT sooner and keep the area under the curve exactly the same as if it was for 105 volts. There we turn it on later, but if you did the math, the area under the curve here would be identical to this. The area under the curve on both of these is exactly the same. So that is the only control of a square wave we have on a DSE system. The CVT or ferroresonant transformer does all of our current limiting and our voltage regulation. Okay. So that's our DSE system, our ferroresonant system. We also have our DPP system, our PWM, or pulse width modulated inverter bridge. And this is the most common design all over the world just now. And it does use the H-bridge design. Once again, you can see here that we do have the H-bridge, very similar to the motor example that I gave you earlier. Okay. And in this circumstance, we have to use 4 IGBTs, just like we did in the motor example with switches. And what we have on the left-hand side, you're going to have basically your battery connected here, and then connected to your battery back here, you are going to have some form of charger. So you're going to have AC to DC coming in here. That charges your batteries and also supplies power to the inverter, and you have positive here and you have negative here. And what we do is we switch the IGBTs on in pairs. So we are switching A and A on here. And you can see that the power flow is down through that one there. That makes this side of the transformer positive, and we get to the negative down through this one here. So we make that negative. So if we were just going to send a square wave to this, that would give you the positive half of the square wave. There's a 0 volt line there. Okay. And then the clever thing, just like reversing the direction of the motor, what we do, we've still got positive at the top and we've still got negative at the bottom. But by switching IGBT-A off and by turning IGBT-B on, if you follow this down, we are now going to this side of a transformer with the positive. And then that goes, the negative side is connected to that side of the transformer through the bottom IGBT. So that makes that negative. So that now, there's a 0 volt line. That, if it was a square wave we were doing, it would now give us a negative going square wave. So all we do is turn A and B on. And if we did that at 60 hertz, it would give you a 60 hertz square wave. Quite simple. And there's just an example of red is the positive half and blue is the negative half of the square wave being created. But we're not creating a square wave in a PWM system. We are using pulse width modulation. Sounds like Star Trek. And I'll explain what pulse width modulation is. Now, modulation, if you go to Wikipedia, which everybody does, they search Google and Wikipedia usually comes up first. It is In electronics and telecommunications, modulation is a process of varying one or more properties of a periodic waveform called the carrier signal with a modulating signal that typically contains the information that we need to be transmitted. So obviously the easiest way to look at this is radio. So for AM radio, which is amplitude modification, we send a carrier signal and then we send the music on top of that carrier signal, which is the modulating signal. And then for FM, it's exactly the same. And we'll go into what AM does, what FM does, and then what PWM does. So here is AM, amplitude modification. Now, if you look at this carrier signal, the frequency of this does not change. Okay, this is a set frequency and its amplitude does not change. Okay, the carrier signal is a carrier signal. Nothing changes. The only thing that changes is the modulating sine wave signal. Now, we've made it easy. We've just done a sine wave here. It's not a complicated music or somebody speaking. It's just a sine wave. And all you're doing is adding them together. And basically what you can see here when we use amplitude modulation is as this starts to go up, the amplitude of each sine wave gets bigger and bigger. And then when it starts to come down again, the amplitude starts to go down. And when we go negative, it gets smaller and smaller, and then it repeats the process. But if you look, my drawing is going to be terrible, but that, I knew it was going to do that. All of these pulses or sine wave peaks are the same. They don't change. There is no change in the frequency here. All we're changing on that bottom AM signal is the amplitude, how tall the peaks are. And that is how AM signals are created and sent out on the radio towers. And for FM, we've got exactly the same carrier signal again. Now remember, it's not changing its frequency at all. And it's not changing its amplitude at all. All we're doing is adding, once again, a sine wave carrier signal, just to make it easier for you to understand. And you can see here on this one, when you go more positive, it makes the frequency different. You can see, you know, we've got 1, 2, 3, 4, 5 here. You can see the pulses, the width of the spaces, not the pulses, the width of the spaces between these peaks is changing. That means the frequency is changing. We're not changing the amplitude of the frequency modulated signal. We are only changing the frequency of that waveform. And that is what an FM modulated signal is doing. And we send that out to the world, and then basically your stereo will remove, it will have a circuit to remove the carrier signal from this, and it will leave the modulating signal for your listening pleasure. In the PowerPoint presentation, this actually moves so you could see it, but unfortunately within Webinar Jam, that doesn't work. So I'm just going to skip this. It's just both of those waveforms together, and you could see it all move as it went along. So hopefully that's explained AM and FM. And now we're going to explain pulse width modulation. And what we do with pulse width modulation is exactly the same as what we did with the frequency modulated signal, but instead of changing the frequency between each waveform, the frequency is going to remain exactly the same. What we are now doing is changing the width of the pulses. So if you look at, let's look at this top here. Forget about the sine wave at the back, because that's just a representation of the average mathematical voltage of the pulse width modulated signal, the green signal in the background. you can see that this very first pulse here is extremely thin. You can see it's just a line basically. And then when we get into the middle of the modulated pulse width modulated signal, you can see there that the pulse is actually quite wide. So you can see that's the pulse there. Obviously, that's supposed to be arrows. Let me color it in so you can see it a bit better, hopefully. Oh, my coloring in is terrible. But you can see that is a much thicker pulse than the one at the start and the one at the end, which is very, very thin. We're not changing the frequency. If you put a frequency meter on here, all of these pulses are exactly spaced apart from the center point of each pulse. Okay, the frequency is not changing. It's only the width of each pulse that changes. That's what pulse width modulation does. We don't change the amplitude. We don't change the frequency. We're changing the width of each individual pulse. And what that allows us to do is it allows us to regulate the output of the system very, very tightly. If there was a current demand or we needed to change the voltage of the output of the inverter for any reason, all we have to do is change those pulses in real time, and we can regulate the output of that system without a ferroresonant transformer and have extremely tight regulation going out of our inverter bridge. Okay. So the diagram below shows what the output of the H bridge will look like on the primary side of the output transformer. So the red PWM is the positive side of the synthesized sine wave, and the blue is a positive. And you can see much more easily here that that is a big, wide, fat pulse in the middle there, and it's a very, very thin, tiny little pulse there. Okay. And the interesting thing is, actually, let me go back. If you took a mathematical calculation of the area under the curve for each of those pulses, it does represent relatively, in mathematical terms anyway, a sine wave. And what we do to clear up all of the gaps and pulses in between is we put that through a choke, a transformer, and a capacitor on the output, and that changes the PWM on this side into a beautiful sine wave on the output. Okay. And that is what an H bridge looks like inside of one of our UPSs. Once again, extremely complicated because we got our control board down the bottom here, and there's other ancillary circuits connected here. But this at the top, this is our H bridge. And let me just show you where the H is. We've got that, and we've got that. And then the H on this one comes off here, goes through the transformer, and then it comes back on here. Okay, so that through a transformer is actually doing that. I know it's hard to see, but that is exactly what it's doing, and that's what gives you the H arrangement. Okay. Now, similar to the DSE system, when we need to have a higher powered system, we can put two IGBTs in parallel. So remember, we had A. Let's make this one A, and let's make these ones A, and then let's make these ones B, and these ones B. Instead of having one IGBT, we've now got two IGBTs connected in parallel. Okay, it's just to give us a higher current capacity on the output of the system. It basically, the gate drive circuit, the gate drive circuit is sending. It's exactly the same signal being sent to both IGBTs, so they both turn on at exactly the same time, and they both turn off at exactly the same time. Here is our positive. So we've got our positive there, and we've got our negative down here. Okay, and if we follow it through, if we turn A on, let's turn A on, power flows down through these IGBTs, down through both of them. Okay, and then there's a bus bar connected here that is connected to this wire. That wire goes out down here through this transformer here. And then that then gets to the negative by going down here through these two IGBTs that are connected in parallel down to our negative circuit here. So it is a bit more complex to look at because the control board and everything else is there, but we are creating a PWM signal. And in an AMETEK solid state controlled DPP system, we are switching our IGBTs at about 8 kilohertz. So think about that for a second. What does 8 kilohertz mean? That means those IGBTs are switched 8,000 times a second. 8,000 times a second. Okay. So we're switching these on 8,000 times a second at the same time, and then they get turned off. And then we switch on these two at 8,000 times a second. Okay. And we just go back and forward, A, B, at 60 hertz with an 8 kilohertz PWM signal. I hope that makes sense. Okay. Actually, let me clarify that. So the frequency of the pulses here is 8 kilohertz, but the frequency of this portion is 60 hertz. Hopefully that makes sense. Okay, so all of the pulses is 8 kilohertz, but the outgoing synthesized sine wave is 60 hertz. Okay, so why have two technologies? And that's a very good question. What I'll do is I'll explain the benefits of the DSE inverter bridge, which is the system that has the ferroresonant transformer in it, and then I'll do the same for DPP. So the benefits of the DSE inverter bridge is it's a simpler control circuit. The circuit basically tells the IGBTs to switch on and off at 60 hertz in North America, 50 hertz for some of the other places in the world. There's really no other complex regulation circuits such as current limit, voltage regulation. The control board is quite simply saying IGBTs turn on and off at 60 hertz. No other complex stuff whatsoever. The transformer does all of the complex regulation on the voltage and current limiting. I know that's hard to understand, but the transformer is designed in such a certain way that even if you put a short circuit on the output of a ferroresonant transformer, the inherent, what's the word that I'm looking for? The inherent makeup of that transformer will prevent that short circuit from damaging the system, and it will limit the current into that short circuit. Number two, another benefit, is it's robust. The regulation is performed by the Ferro CVT, which has an 80-year-old technology. They've been around for ages, and they just work. They work all day, every day. You know, actually, I was just speaking to one of our service engineers last week, and he was at a system that is still running at a plant that is 40 years old, still running without any issues whatsoever. So they are very, very robust systems. They also have excellent fault clearing capabilities. The transformer can supply in excess of 500% of the rated current for a very short time. So let's say you have a 10 kVA UPS. That transformer will give you 50 kVA of energy to clear any short circuits if necessary. So they're very, very good at clearing faults on the load circuits if necessary. The CVT also has stored energy, which will supply power to the fault. The energy in the transformer supplies the power, and we can shut the IGBTs down quickly, and that prevents IGBT failure in many cases. Not every case, because I've told you before, the IGBTs are very, very sensitive. But It is designed in. As soon as we see an issue, we shut down the signal to the IGBTs, and then the stored energy in the transformer will supply the power to the fault, clear the fault, and you'll probably transfer to bypass in that short period of time, and then you can go back to inverter. But we're trying to protect the IGBTs in that case. And the bridge design has been proven reliable for many decades. Okay, there's only 2 pairs of IGBTs in the center tapped bridge ferroresonant design, and it's just one on, one off. Very simple, and it's very difficult to get shoot through on that circuit. Very robust, tried and tested. That is the advantages of the DSC. One of the benefits of the DPP, the pulse width modulated inverter. Well, first of all, it's modern technology that provides a near perfect sinusoidal waveform with much tighter regulation. So the sine wave that comes out of a PWM system, it has extremely low THD, harmonic distortion, and when you put step loads on it, the regulation on the output waveform is extremely tight. We can really control that waveform very quickly and give you excellent regulation. DPP is more efficient. One of the downfalls of the ferroresonant design is that we have to saturate that transformer, and that takes energy. That transformer is saturated all the time, so that's kind of wasted energy and heat. But with the DPP, it's more efficient. We're not energized, well, we are energizing the output transformer, but we're not saturating the transformer. We're not wasting energy, as much energy in heat in the inverter bridge design. It's also got a smaller footprint due to not needing a CVT, which is a rather large transformer. So, and also a smaller filter is required because the PWM is so similar to a sine wave. We don't need as many capacitors as the ferroresonant system needs. Also a wide range of alarm options and monitoring points as part of a standard package. Because it's much more electronic and much more up-to-date, the DPP system, we can do so much more monitoring of that system. Also, it gives you greater flexibility for communication, especially Modbus, Ethernet, Internet, all those kind of things. For the DPP, it's all built into the design of the main control board, where you can have Modbus, TCP, whatever you need to connect to the outside world. And lastly, the DPP has better dynamic response to load steps, which I mentioned earlier. If you slam a load onto a DPP system, it's going to react very quickly. It's going to widen all of those pulses in real time. And the dynamic response, in other words, how the voltage dips when you put on that load, it will be much less than a DSC system. Okay, so there are advantages to both designs, and they are both excellent. It just depends what you are looking for. If you are looking for tried and tested technology and you have a bigger space and you don't need as tight regulation and dynamic response, then a DSC is absolutely perfect for you. Okay. If you're looking for a smaller footprint, more efficient inverter that has better regulation and dynamic response than the DPP, is the way to go. It just depends on what your application is. Okay, and look at that. Wow, I have finished 6 minutes early. It's a record. So now I would ask, if you have any questions, please, the best place to put them is the Q&A, but if you want to put them into the chat, that's absolutely fine. I'm going to have a look through the Q&A and see what I can find while anybody else asks any questions. And in truth, it doesn't have to be related to this particular presentation that we've just done. If you want to discuss something else, you have a question on, I will quite happily try and answer that for you. Can you further explain the purpose of the choke in converting the PWM signal to a sine wave? What a choke does is kind of inverse to what a capacitor does. I don't know if I can go back to the slide here. Yeah, here we go. So a capacitor charges and discharges with respect to voltage, really. If the voltage dips, then the capacitor will fill in that gap in voltage. Hopefully that makes sense. What an inductor does is it does the same with current. The inherent properties of a choke or an inductor is that it does everything it can to try and keep the current flowing through it the same. Okay, so if there is any fluctuation in the current flowing through a choke, basically the field collapses and it builds up a voltage potential across it. And in doing that, in tuned with the capacitor, they together fill in all the gaps and smooth it out to a sine wave. I really can't go into any more depth than that because it's extremely complicated and there is some math involved and it's way above my head. But that's really in the basics of what a choke and a capacitor do together, or an inductor and a capacitor do together, is they smooth out all of those PWM signals into a nice sine wave by either resisting a change in voltage or resisting a change in current. Okay. So that's all we have in the Q&A just now. Let's have a look what's in the chat. Could you explain in more detail what the fault clearing capabilities are used for in the Ferro CVT? Very good question. It's just an inherent property of a CVT, but it comes to our advantage. And let me see if I can present this in a way that's relatively simple. When we make UPSs, we know basically that the output of that UPS is going to be tied to an AC distribution panel. Okay, so let's take a 10 kVA UPS or inverter, for example. Now that's going to give you around about 83 amps as an output. So that's going to go to your AC distribution panel, and you are going to have maybe 10 circuits connected to that. So those 10 circuits are probably going to be protected by a 10 amp breaker, something similar to that. The problem with a 10 amp breaker is that it can take up to 5 to 10 times the required current to trip that breaker very quickly. So if you have a short circuit on one of those breakers, you need the inverter bridge to be able to, well, you would like the inverter bridge to be able to supply that large amount of current to that particular circuit so that breaker will trip and none of the other circuits on that AC panel will trip, and that the voltage doesn't dip in such a way that it causes the other loads connected to that AC panel to be affected. Now, let's say in that 10 kVA example, you have 30, maybe 40 amps of standing load connected to all of those MCBs in the AC panel. That means you've only got 42 amps left to supply to a short before you overload the inverter bridge. And that may not be enough to trip that breaker quickly. So in an IGBT inverter, what we have to do is try and protect the IGBTs from blowing up by seeing high current. And in the PWM system, all of the current on a fault will be seen by the IGBTs. So we don't want that to happen. So what will happen inside a PWM inverter is it will see the high current going to that fault. It will immediately transfer the system to bypass. The bypass supply will come from a transformer in your MCC, and that is a very robust, stiff power source, and that will supply a lot of current into that short circuit, which will then trip that breaker, and then when everything is good, you can transfer back to inverter. Okay, we're protecting the IGBTs. But if you remember, I mentioned that in a CVT, a ferro system, there is stored energy in that ferro transformer. So what we can do is we can actually switch the IGBTs off, but there is still going to be 500% worth of stored energy in that transformer that can go and clear that breaker without having to, with maybe not having to transfer to bypass. In truth, most of our systems are designed to transfer to bypass in a fault circumstance to clear that breaker because it's the safest way to do it. But for example, if you didn't have bypass available when that fault occurred on a CVT system, that will push that current through that breaker without any issues and trip that breaker. So they are much better. A CVT transformer is much better at clearing a fault because we don't have to involve the IGBTs in that process. Okay. Okay, another question in the Q&A. How does the pulse get modulated on the inverter? It's unfortunately, it was too much information to put it into a presentation like this, and in truth, it's just extremely complicated. The control board basically uses complicated circuitry that creates a low voltage pulse that goes to the gates of each IGBT. But that low voltage pulse is identical to what we're going to get out of the system. So it's basically the PWM is generated using complex circuitry on the control board. That then goes to a gate drive board, which provides isolation between the control board and the IGBTs, because the control board only wants to see about 12 volts on it. The IGBTs are going to see maybe 130, and in some circumstances, 240 volts DC. So we want separation between those two. So the gate drive board gives us separation. And then the gate drive board also adds some power to that signal and then basically replicates the exact same signal that the control board sent, but it is a more robust signal that goes to the IGBTs. But basically, it's a complex system that is generated on the control board using a basic feedback network and a pulse width modulated generator chip and phase lock loops and many other complicated things. So I can't go into it. And then do you simply control how long each switch is closed? Yes, absolutely. My long-winded answer didn't see the second part of your question. And yes, in all of our IGBT inverters, all we are doing is opening and closing the switches. That's all we're doing. We send a signal to the gate to close it. We remove the gate signal and it opens. Simple as that. On and off. Okay. I'm going to take this time now. There doesn't seem to be any more questions. If you have any, quickly type them now because I'm signing off. And if I see something pop up, I will answer it. But I would really like to take time to thank you for spending 1 hour of your day listening to me babble on about inverter bridges. I do know that your time is very precious. You're very busy people, and I do appreciate you taking the time out of your day and spending it with us here at AMETEK Solidstate Controls and explaining how our inverter bridge works. You will be sent a survey as part of registering for this, and I know how you feel when you get a survey. Nobody wants to fill out the surveys. It's a pain in the butt sometimes, but in that survey there is a question that asks, what would you like us to discuss at the next webinar? Which subject or topic would you like us to discuss? I look at every single one of the surveys, and I really like to see what you want us to discuss, because there's no point in me just always discussing things that I want to discuss, that doesn't help you. If you have specific things that you want us to discuss at our next webinar, please fill out the survey or even send an email, which is going to get posted in the chat here very soon, on how you can contact us. Brooke has already put in the chat bar how you can go to our YouTube channel. There's the link there that takes you to the channel, and then by tomorrow afternoon this presentation will be uploaded and you can view it. You can test that link and you can see all of our previous webinars on our YouTube channel there. And there Brooke has just typed in, you can go to our website, go to our contact us page, or you can email us at sci.marketing@ametek.com, or you can even pick up the phone and give us a call, 1-800-635-7300. You will go through a menu system, but you will speak to a human when you call that number. So we do like you to contact us and let us know what you want us to discuss in the next webinar. And there's one other thing put in there. Do we have PDHs and CEUs for our webinars? We don't at this moment in time, but we are looking into and thinking about how we can go ahead and offer PDHs and CEUs for our webinars. But we haven't got anything in place at this moment. So once again, thank you very much for taking your time out on this Wednesday, May 18th, and I appreciate it. And take care until next month. It's going to be probably the third Wednesday. As always, look for your inbox to tell you when it's going to happen. So thanks again. Take care. It was a pleasure speaking with you today.